composition changes according to the temperature. And when you change your temperature, say that you have a casting solution at this A point, and your membrane will become, and membrane formation will follow as you decrease your temperature to a coagulation bath and follow this line. And this is the B point is imaginary points, where the B prime and B double prime will be the actual point for your polymer lean phase and polymer rich phase. So the polymer rich phase will be the membrane that you are looking at, the polymer positions, whereas the B prime will be the position where your pore will be forming anyway. This A to B will follow these two lines, where the green line, the upper line of this green portion, will be defined as bimodal the lines, whereas this, the line, upper line of this, the red portion is called the spinodal line. And between this spinodal and the bimodal, the green area is called the metastable region. And the metastable region is the one that this is the stable region, but you start to have a nuclei, and the growth of this nuclei, thank you, growth of this nuclei, and that's what we call this metastable region. And you have your stable region and stable region as well, up to the point where you have the green region, and this red region is unstable regions. Okay? So we will talk about in more detail about the thermodynamic point of view. So if you take a look at the this picture here, actually this was taken from Strathmann's the chapter 3 on the polymer membrane preparation and characterization, and you can take a look at it in more details. Okay? When we are talking about the phase separation, we need to talk about thermodynamics, and the Gibbs free energy mixing of this, the delta GM is defined as delta H minus T delta S, and for the mixture to become miscible each other, then the Gibbs free energy mixing should be negative. Okay? When you look at this curve here, this is the Gibbs free energy change of Gibbs free energy mixing changes, delta GM, versus the composition of your binary mixture, where this in the x-axis, left-hand side will be the 0 to 1, and this is the x2. 2 means a polymer. And when you have the polymer and actually the solvent and polymer, the perhaps number 1 means that you have the solvent, and number 2 probably will be the polymer. So your polymer content will be changing as a function of the Gibbs free energy mixing here in this case in the y-axis, and another y-axis is the delta SM, and delta SM again is plotted here. So delta SM is always positive, as you can see here, whereas delta GM is always negative when you have a spontaneous mixing of your mixture. Right? When we take a look at this line, this is the chemical potential, and the chemical potential, initial chemical potential will be the mu1 0, okay, and mu2 0 for the component 2. For the component 1, this is the chemical potential. This chemical potential as well. So free energy mixing delta GM is always negative when you have a spontaneous mixing, okay? And delta SM is always positive, whereas delta H is relatively the 0 if you have ideal mixture of the binary mixture in this case. So with this system, I think it will be very useful to describe what's happening in our the mixture mixing cases. Now we can take a look at the delta GM with X2 again, but we can describe in some of the points, because this delta GM could be related with the chemical potential, of course. And if you divide this by the X, here X might be X2, then that's called the chemical potential. Okay? When the chemical potential is defined, then this is the first derivative. And if you have a second derivative of Gibbs free energy mixing into the X, then it will be the change of the chemical potential as a function of your the X. Okay, again, and we'll take a look at what happened in the case of zero in this case. But that's the definition of chemical potential of the two components. Now let's say that we have this region. Okay, this is this boxed region at the two extreme H is the case where you have a stable composition. Stable composition is the one that you have, let's say, one that you have a stable composition here. Okay? This is the stable liquid phase, whereas this is the unstable region. And this green line again, green region again is a metastable the region. Metastable means stable, not unstable, but stable, but it's not the same as these are stable regions. Okay, okay, so we can describe what are the metastable regions in terms of the membrane formations. So first of all, we can take a look at the stable region. In this case, delta GM is a negative because it's a stable region, and the two components are completely miscible in this case. Okay, two components, binary mixtures are completely miscible in two extremes. Okay, when you have a large component of the polymer, or the small component of your polymer. Okay, when you have a larger, the component of cases, we have very stable binary mixtures. So in this case, we have a negative Gibbs free energy mixing. Delta GM is negative. And we can take a look at the opposite cases where we have a positive Gibbs free energy mixing, and this is the region where we have unstable region, and this is the red portion, red area, and you have pretty much the unstable. That means that your delta H could be positive, where you have because delta GM is GM is positive. That means that delta HM is much more larger than T delta SM, because delta SM is always positive. Okay, so the absolute value of delta H versus the T delta S is the problem to contribute to your negativity or positivity of your delta GM. So if you have the positive delta GM, then you should have always much higher delta HM, meaning that the enthalpy change of each component, one or two, is pretty high, so that their interaction is much more contributing to the whole systems. So this is the region where we have unstable regions. Okay, and then between these two regions, unstable and the stable regions, is called the metastable region. This metastable region is the stable region. Okay, is stable because we have a Gibbs free energy of mixing is negative, so that we can say this is the stable region. But microscopically, this composition of the mixture begins the nucleation, which is different from those two extreme stable cases. And you have a nuclei that is forming in this metastable region and grow, so that nucleation starts, and the growth of your crystals, the growth of your the polymer cases. And the mixture, this nuclear maybe decomposes in these metastable regions. Okay, so when you have a derivative, so this is the case where we have when you just draw the line, and you have some points between the derivative of delta GM with with XM X2 is equal to this point, and you have inflection points. So this is located with the minimum Gibbs free energy mixing of this curve versus the inflection points is called the metastable regions. Now, when you take a look at the experimental determination of your this point, the bimodal point and the spinodal point is that when you try titrate, let's go back to our titration curves. Okay, I think we have a titration curve. Okay, if you think about this case, we have a polymer solution, okay, stirred polymer solution, containing polymer and solvents, and you drop your non-solvent from your pipettes, okay, and at some points you do not see any solid particle in your polymer solutions. Okay, when you slowly drop your non-solvent, initially you do not observe anything, right? Because it's too simple, too small. But later, when you have a drops by drops, after some time, then you start to see white, appearance of your drops, white, so color changes, but it disappears very immediately, right? And that's the point where you start to have your bimodals. Okay? Your phase changes, but you start to have your bimodals. It may grow. It may grow. That's the point where you have a nuclei and grow, but it disappears immediately. Okay? But later on, when you drop by drop, you start to see your white milky particles, but it disappears. But after some time, all of a sudden, you observe the precipitation of your whole solution, right? And that's the point where it passes to the spinodal point, so that you reaches the unstable region to become solidifications. Okay? So this is the experimental observation, but we can describe this observation with the theoretical aspect here in this case. So we just pass the stable region. When you add your non-solvent, okay, then your composition of the X2 might be decreasing, but you increase your X1 so that it follows some line over here, okay? So that you start from your right-hand side, you pass, and you start to see the milky phenomena, and all of a sudden it will be you reach a precipitation in this case. So we can describe the interface between the stable region and metastable region as bimodal points, and the metastable region between the metastable region and unstable region is called the spinodal points. Okay? Spinodal points. So bimodal point is the one that your chemical potential defined as delta GM divided by the X derivative. Derivative is zero. It's called the bimodal point. Your second derivative of a Gibbs free energy mixing with the composition is called the spinodal point. So we can say that the first derivative and the second derivative, okay, first derivative and the second derivative of Gibbs free energy mixing as a function of the composition is related with the chemical potential difference, as you have already seen. So if we redraw this Gibbs free energy mixing curve versus the composition as a derivative, first derivative and second derivative, you will see that if it's zero, this is defined, each point is defined as a bimodal point. If the second derivative is equal to zero, it's defined as a spinodal point, right? And this way, you will be able to, define and describe theoretically, thermodynamically, the spinodal points and bimodal points. So again, if you go back, and this point is spinodal of the bimodal point. This is the spinodal points. And again, we can take a look at the temperature versus the composition curve. This is the bimodal point. This is the spinodal line, as you have already seen. Okay. Okay. So if you describe the thermodynamic aspect of the tips, we can start from a point where your mixture, polymer, for example, PVDF and the diluent or the solvent is mixed together, and if you increase the temperature, it becomes a liquid phase. But if you decrease your temperature, okay, it starts to crystallize, starts to form a nuclei and grow. At some point, it just crystallizes everything, and because you lower your temperature and passing your unstable region and form your polymeric phases. This B point is called the imaginary point, but you have a polymer lean phase and polymer rich phase. Polymer rich phase means that you have more polymers in your membrane system, whereas you have pores, which is the point where you do not have any the polymers, but imaginary point might be the polymer lean phase and polymer rich phase in the thermodynamic way, and it's called the XP1 and XP2 and XP2 for the binary points, where which is a stable region, and you have XP2S here in this case. Okay. Now we have some points where we have a critical points here. Critical point is defined as the point where you do not have where you have a binodal point and the spinodal point is about the same. Okay, so you do not have a time for your nuclei to grow at the critical points. But if you pass the other lines, something like this, okay, then you form the nuclei, and by lowering the temperature means that you have some time to lower your temperature, because you always lower your temperature as a function of the rate of your cooling. Okay? Rate means time, so that the decreasing temperature will always take some time, meaning that you form the nuclei, you have some time to grow your nuclei to become crystals, okay, or polymers. If you pass the other line, then it's different from some line the passing your critical points. Now, we knew that the nuclei is governing the membrane formation, particularly in the TIPS cases, and the size of nuclei might be important, okay, depending upon your polymer concentrations, of course. Okay. Nuclear size is opposite to your degree of what they call the supersaturation, meaning that you have if you lower your concentration, then your nuclear size might be the smaller, whereas nuclear size might be larger when you have the polymer concentration, which is high, which is lower in this case. I'm sorry. So this is the opposite trends for nuclear size and degree of the saturation or the polymer concentration, as you can see here in this case. You have some more discussion in this chapter 3, particularly in the Strathman's book, in terms of the NIPS. But I think you can take a look at what's going on, at least on the TIPS case, and you can take a look at it a little bit more. Or if it's unclear for you, then you can take a look at these chapters. So practically, what we observe is this curve, and this is what we call the phase diagram, the real phase diagram. The phase diagram that you have seen in the TIPS or NIPS, particularly the TIPS, is a theoretical ones, but this is the practical phase diagrams. What they have observed is that this is the effect of polymer concentration, polymer weight fraction with PVDF in your dope solution. For example, if you have a 20% polymer concentration, that means that you have a 20% polymer, and 80% might be diluent systems. Okay? Here in this case, we have DBP or DOP, dibutyl phthalate or dioctyl phthalate, has been widely used to make the softening of your PVC. Okay, polyvinyl chloride. Polyvinyl chloride is a very useful component, but it's very the rigid material because of the dipole-dipole interaction between the chlorine and chlorine in your side chain of your vinyl polymers. This chlorine has 3 unshared electron pair, rich in electrons, so it interacts each other. So it forms some sort of honeycomb structures, okay? Imaginary honeycomb structures. So it becomes a very rigid rod-like structures of your PVC itself. If you add this plasticizer, what happens is that your octyl group or butyl group in your phthalate will bother the interaction between the chlorine and chlorine, so that this alkyl group is inserted between the chlorines, and it blocks the interaction between the chlorine, so that your dipole-dipole interaction will be much more reduced. Therefore, by adding these components, your material will become softer, okay? Flexible, PVC. Okay? So DOP and DBP has been used for a long time as a plasticizer of your polyvinyl chloride. Okay? Now, PVC itself, you can make a tube. You can make water transporting tubes, which is very rigid. But you can make a PVC as a flooring of your, particularly in the Korean, the household. You have a pretty softer vinyl, what we call the vinyl flooring, or vinyl the wall papers, or vinyl the wraps. Even the wraps could be made using this technology. But be careful that DOP and DBP is again the carcinogen. Okay? So it was banned a long time ago, but still, in large the small industries, large number of small industries still use this DOP and DBP in many cases. But anyway, they use in 2006 they used DOP and DBP as a plasticizer or as a diluents in PVDF because melting point of this DOP and DBP is much higher than the temperature of mixing, so that if they increase the temperature up to about up to about 180 degrees C and decrease the temperature, so that they found that the cloud point is about this case, and they found that the crystal point is following this line. Okay, so this is the two very important aspect of the compositions. And so the composition of the polymer, and membrane morphology is influenced by two factors. First one is about the concentration of a PVDF. In other words, composition of the polymer and diluents, okay, and temperature of the cooling bath. In other words, when you increase the temperature up above 100 degrees C, how fast you cool down your polymeric system will influence the formation of your nuclei and time to grow your nuclei. Okay? So that will influence the final morphology of your membranes in this case. Anyway, this is the real, if you change the plasticizer from DOP, DBP to others, then you have a different, the phase diagrams in this case. Using these typical phase diagrams, you can cast your membrane in the fleshy form, or you can spin your hollow fiber by the TIPS process. And the use of this TIPS process, or advantage of this TIPS process, is always about the mechanical strength of your polymers. Okay? Because if you compare the NIPS hollow fiber system and TIPS hollow fiber systems, NIPS does not induce much on the crystals, whereas TIPS process always induces the crystallization of your polymers. And the crystallization of your final polymer will influence your mechanical strength of your membranes. And one of the greatest advantage of this TIPS process is the mechanical strength. Okay? You can make a strong fiber even from the same polymer. You can make a strong fiber from TIPS out of NIPS process, okay, or over the NIPS processes. So we have a critical point, and again, this is the real point. And when they use the fluoropolymer, this is one example of the fluoropolymer. I do not have time to, explain to you about the details about these polymers, but it's the fluorinated hydrocarbon polymer from Solvay. And what they have done was, this was published in 2002. What they have done was, by changing the composition, just like a PVDF case, we see the temperatures. And temperatures was increased above the 180, 190 degrees C. And this is the stable liquid region. You have a solid liquid region, or liquid region in this case. And you have critical points here, which is defined as a point where your bimodal and the spinodal is touching each other. Okay, experimentally it's difficult to measure. Reproducibly, it's difficult to measure binodal point and the spinodal points, but you can see by changing the composition, you see this line here. This is the crowd point line, and the maximum, the phase diagram crowd point line is called the critical points. And the critical point in this case might be about maybe 12%, 30%. I think it is written here. Yeah, about 12% is defined as a critical points. When you increase your polymer concentrations, then your phase diagram is a little different. A crowd point is different, so that your point following this line is called and the inflection point between this line is called, about 25%, is called the monotactic compositions. Monotactic composition of your polymers. So when you have a casting your polymer starting from A, A point, then where you follow your cooling is very important. Whether you follow this line or this line or this line will make you a different morphology of your polymers. So the phase diagram, drawing of the phase diagram is the first step to go ahead with the TIPS process. Now we can see two pictures. First one is the effective temperature. When you cast your membrane at low temperature, lower than your the crowd point, or close to your crowd point, will make a different membrane morphology. And we can see what happened in this case. And when the casting temperature is lower, whether you have polymer concentration is about 16.5%, then if you have a lower temperature casting, then the monotactic points, where the refraction points, then you have a very small pore sizes. You have a very small pore sizes, whereas if you increase the temperature, then you have a little larger pore sizes in this case, even on the surface of your membrane. So if you wanted to make a porous membrane, what you wanted to do is that you increase the temperature so that your heat transfer rate should be minimized to make the polymer to become crystallized in this case and make your porous membranes by increasing the temperature of your the casting solution. So by changing your dop composition and changing your starting point, okay, you will be able to make the porous or non-porous membranes using this TIPS process. Okay, there was a general description about what's happening in the Gibbs-free energy mixing for your TIPS cases. And we can also see NIPS cases as well. Right? So this was the second description of the phenomenological phenomena of the phase separation process. I think this is the same as what we have seen before. Again, the phase diagram is very important. You can have two phases, dealing with the two phases, and the two phases might be miscible, might be separated each other in the two phases. So this way you can make a membrane. But this phase diagram does not tell us about what about the finger-like structure or the sponge-like structures. But this phase diagram will tell us about the porous membrane or non-porous membranes, okay? Not the fingers or the sponges. Fingers or sponges might be attributed to the kinetic factors rather than thermodynamic factors, okay? Because you already have seen how fast the non-solvent with moving, as we have already seen in our microscopic videos. So if we summarize, we can make a symmetric membrane. We can make a symmetric membrane. We have both polymers and inorganic materials. We can have very homogeneous films, dense films. We can have finger-like pores or sponge-like pores. We can make asymmetric structures with the same polymer, which is called the integrally asymmetric membrane. Or we can make a composite membrane with two different polymers or three different polymers. Okay? This is what they call the composite membranes. So I think you can see the same pictures that I have shown you in this next few more slides, and I will just go quickly over through, except some of the industrial membrane processes or membrane pictures. Okay? This is the dense membrane. This was what we call the evaporation of the solvents, and you can make a porous membrane by phase separation induced by the water vapor. So this is the example of a BIPS process. You can make a very nicely done high definition polymer membrane with a 3D lithographic channels. But again, this has not been commercialized yet. This is still in the process of in the laboratory. You can make this type of very neat membrane by using lithographic channels. You can make this type of membrane with a block of polymers again. Okay? Or you can make a very nice channels. And nice channel is very important because you have a very narrow pore size distribution and the very the similar in the channel length as well. You can make a hollow fiber by phase separation. You can make a asymmetric membrane as well, whether you have a porous membrane or asymmetric membrane or composite membrane, whatever you like. Again, I think this has been already touched upon. Solvent, polymer, additives. You can make a flash sheet, or you can have the integrated skin membrane. In industry, in order to make these flash sheet membranes, what you have done was you have a casting solution or dope solution cast on top of your generally the non-woven support. Non-woven porosity of the non-wovens or the type of non-woven is very important. And the casting solution is of course important. And this was cast on top of your non-woven fabric. And this was immersed in the coagulation bath and taken out and passing through this washing bath and drying to make a roll-up of your membranes. Although the scheme is simple, you have a lot of arts, a lot of try and errors, a lot of the theoretical aspects to consider, which is not easy. Okay? And you need a lot of efforts to make the nice membrane out of these systems. You can make a hollow fiber systems. Again, you can have a spinneret. You can have a spinneret. The spinneret may have 2 holes. One hole will spin the polymer solution. And the second hole will go, particularly inside, is called the ball solution. You can have a dual layer systems, dual layer hollow fiber systems, where we have 2 polymers that cast together using the triple jackets instead of double jackets, double spinnerets. So by designing the specific the spinnerets, you will be able to make the just a hollow fiber with the same membrane, same polymer, or you can have a dual layer hollow fiber systems. Again, although it looks very simple, you have a lot of efforts. You need a lot of efforts to make a nice membrane because you have a lot of parameters to control. Again, just like the case of flash sheet membrane as well. Okay, so we can have a hollow fiber, which is not very good, in good shape, but in industry, this is one of the examples of the hollow fiber membrane manufacturing systems. You have a hollow fiber spinning machine back there, and this is the take-up, final take-up, the region, and you pass the washing bath, you pass the drying ovens. And finally, you just take up, something like this. And this is not the only one. In order to make a hollow fiber modules, or the spiral wound modules, you have to cut them. You need a lot of efforts. Although in some cases it's automatic processes, you need a lot of manual manufacturing systems for the modules. Okay? It's like a fiber manufacturing process. You just take up from the drying ovens, But still, even after drying of your polymer membrane, hollow fiber membrane, you may still contain small amount of your residual solvents. But residual solvents, contents of a residual solvent should be controlled, and because if you have a residual solvent remaining in your membrane before use, then it will affect your final performance of your membranes, because it may reside or it may be gone during your shipping process or transportation process, so your performance might be different. So residual solvent control is very important. So there is a special treatment process after this take-up of the membrane. When you have a take-up of this larger roller, then you have to cut them in a desired size, so that this was again stacked together and shipped to the room where you need the aging of the fibers, and then glue them and cut them and put it into the tubes to make modules. And I don't think we will be able to take a picture of this manufacturing sites, but it's nice that you can see these pictures. TIPS process needs a latent solvent which can take the latent heat so that you will be able to increase the temperature above the melting temperatures. And again, because the polymer needs melting temperature, this polymer should be at least a semi-crystalline. Okay? That way you can make the strong fiber or strong membrane out of this. Casting solution could be spun into hollow fiber, or you can cast membrane with the flash type, and so on. But latent solvents should be extracted. Later on anyway. You can make a flash membrane or hollow fiber systems. Again, so this is the polymer materials, starting from cellulose acetate, polyamide, polyimide, polypropylene, sulfone, PVDF, and so on. And membrane processes is written in here. UF means ultrafiltration, microfiltration. RO means the reverse osmosis, gas separation. MC is the membrane crystallization, and D is dialysis. What else? MC is the membrane crystallization, and E is the emulsification, I guess. Oh, electrophoresis. So depending upon the polymer types, the application is quite sometimes limited, and sometimes the variety of applications in case. I think this pictures has already been touched, so I can go quickly. Now, when you have an extrusion and stretching method, you can have a porous membrane by sintering, but you see, it passes through the extruder, and from the gravitational forces, you stretch them and orient them in the actual directions, but perpendicular to the directions, you still have a stretching. You still have a stretching in this way, so that you can have a biaxial stretchings to induce the high porosities. But the rate of stretching between the axial versus the perpendicular direction will make your membrane orientation, the fiber orientation, or the pore orientation might be different. Okay? And this is the case for a stretched membrane of polypropylene. Polypropylene or the PTFE membrane is manufactured by this way. This is the typical example of a cell guard membrane from Celanese. I think this is the PTFE membrane, and these points are gathered together, just like the nerve cells. Okay, and this black part is the porous phases, and you see the clustered regions, just like a nerve cells clustered to each other, aggregates, agglomerates, and this is the point where you have sintered together, sintered positions. Track etch method has two different regions. One is the ion beam bombardment region. Second one is etching region, so that you can make a track etch membrane like here. So although this is very similar to the 3D the lithographic membranes in terms of the size of the pores, but distribution is a little different. Okay, but anyway, this has long been used as a membrane for high purification of the biomolecules, particularly in the medical area. They need a very specific the distribution of the pores to separate the biomolecules, and track etch membrane has been widely used. You see the very nice picture, just like lithographic ones, and you can make the template etching, and what you do is that you expose your UV light or X-ray lithography through these templates, and then you have an exposure region, and unexposed regions. And I think I can show you in my own picture, appeared last year in small, where we can use our polyimide, and the polyimide is very sensitive to UV exposure or the lithographic X-ray lithography, so you can make a very similar the picture like this, and could be used in fabricating the electronic the devices. And after leaching, you can make holes out of this, out of holes, or you can have a very the 3D pictures as well. You can have dynamic membranes with coating, deep coating process. Again, this is the same picture. Composite membrane could be fabricated into two different the structures, and the polymer membrane, polymer structure could vary from polyacrylonitrile, polyamide, or the polyimide, PP or PVDF. The several membranes that we can use, and you see the solubility or the liquid and crystal formation could be defined in different organic solvents, but these are not actually the solvents. Okay, this could be added into the DOP solution. You can make a composite membrane out of this porous structure. The porosity or effective path depended upon your diameter of your pores, or the length of the pores, length of the barrier layers, which will influence the final transfer properties anyway. Composite membrane. Okay, this is the simple description of the composite membranes, and this is the typical example of the thin film composite TFC membrane for the nanofiltration purpose. If you wanted to make a reverse osmosis, then you need to use aromatic diamines. But if you're using aliphatic diamines like this, aliphatic diamines like piperazine, reacting with TMC, 3-methyl chloride, you can have a cross-linked structure with aliphatic cyclic components. The reason why they use this piperazine is that the C carbonyl carbon and nitrogen, C and N group, is the weakest point in terms of the bond strength. But if N is attached to aromatic ring when you're using methylene, the metaphenylene diamines, then the CN bond will be much more easy to be cleaved, so that the CN bond was attacked by the chemicals such as sodium hypochlorite, because sodium hypochlorite is used as a cleaning agent after your reuse of your modules, so that your molecular weight will be decreasing. So membrane life will be much more reduced if you're using the aromatic diamines. But if you use the aliphatic diamines, then the chemical stability is much more enhanced. But the problem is that your selectivity will the rejection will go down, so that in this case, this chemistry has been used for making the nanofiltration membrane rather than reverse osmosis membranes. Anyway, what you do is that you have a porous support, impregnate the liquid 1, and immersed into a liquid 2, so that you let them polymerize them, and if you remove this liquids, excess liquids, then you can have a composite membrane. So this black part is interfacially polymerized area, which is this region, this polymer is coated on top of here, whereas the excessive the solution will be washed out from your support layer, so that you can leave only the polymer, thin film composite polymers. This way you can, and another way of making the thin layer is by using the inorganic composite membrane. Inorganics such as titanium oxide, or if you are using the aluminum hydroxide or aluminum oxide, alumina, this is called the alumina, the powder, or titanium oxide powder. You can make the alpha alumina, or you can make the gamma alumina, depending on your crystal structures. Generally, alpha alumina has a little larger in size of your pores, and gamma alumina has much more compact, so the pore size of your gamma alumina is much smaller. So if you wanted to make a very compact system, you should use a gamma alumina rather than alpha alumina. But if you wanted to have just microfilter or ultra microfilter particularly, then you may use alpha alumina to sinter and make porous membranes. In this case, you can have a Zoll-Gel chemistry. You can use a Zoll-Gel chemistry to make the very thin and dense layer on the top, so that it's much more like composite membranes. Usually, inorganic membrane is treated at very high temperature, sintered above 1,000 degrees C, whereas polymer is not possible to be treated in this case. Okay? Polymer uses maybe lower than 400 degrees C, 300 degrees C, whereas inorganic materials is treated at high temperature, above 1,000, generally 1,000 degrees C. This slide generally describes the Zoll-Gel chemistry. When you have a ceramic powder, you can add the water and binder and surfactants, just like suspension polymerization cases, and you make a suspension, meaning that it's like the wheat powder suspensions, 밀가루 바치한 것 같이 suspensions, and then cast the membrane and dry them, and what you do, what they say is a hybrid organic inorganic green membrane. Green membrane is intermediate. It's not real membrane, but it's a handable membrane. It's like a draft membrane, and then sinter them, and you make a real membrane here in this case. So green membrane, green word is used in the industry, and it's like a precursor. It's not the real membrane, but it's handleable. You can handle this membrane. You do not call this as a membrane, but it's intermediate between the membrane and your suspensions. Okay? So first you make a handleable the green stuff by removing the water in some cases, and then sinter them. When you think about making your porcelain, okay? Porcelain, you can make a final porcelain, 도자기 같은 거, final porcelain here in this case, but when you make a 반죽 or suspension, you first form the 틀, 또 뭐라 그러나? I don't know. I'm not the artist, so I forgot about the words. But you first make a green pot first, okay, which is not. You dry a little bit of the water, and it's not finally put it into the hot sintered the furnace, but you first make a green pots in the mold, and then finally you sinter later to make a porcelain. It's almost the same as what you can see here in this case. The Jolgal process might be divided into several cases. You can have alkoxide in alcohols. You make a colloids or polymer solutions, cast a membrane, and again you make a green membrane and sinter them to make inorganic membranes. In inorganic materials, we have some membranes called the perovskite membranes. This perovskite membrane has pretty good electron conductivity. Okay? Electron conductivity. Electron conductivity is important in some applications, okay? Such as oxygen conducting membrane. We call that as ITM, ion conducting membrane, to make 100% oxygen, and so that we call this a perovskite membrane, and we will see a little bit of chemistry from these perovskite membranes. Traditional ways of making this perovskite powder is that you have citrates, you have solid state and coarse precipitations, but they have different the procedures, which I do not want it to repeat in this case, because one reason might be I do not know much about this. And the second reason is that it's a little bit complicated. And you see, you have a mixture of several components, and depending upon your your compositions, you have different perovskite membranes. But you see, there's a lot of other processes, and finally you sinter them at different temperatures, over or close to 1300 degrees C. But recently, the new method was developed, as described in this slide or in the textbook. You have EDTA and ammonia, water, and mix together, sinter them and heat them at a little lower temperature. So the final composition is BSCFO and membrane, and you can make another type of perovskite membranes. Now I'm handling manuscript, at least 360 manuscripts per year, and submitted to Journal of Membrane Science, and I'm handling more related about the gas and the vapors. And some of the editors are handling some of the topics, like water fouling of the membranes, or fuel cells were touched by Michael. Andrew is dealing with the water. Jared Lin in Arizona State is dealing with inorganic membranes. And he's an expert in inorganic membranes. And I think he's dealing with more on the perovskite membranes, but sometimes some other countries like Iran, they cannot submit the manuscripts to editors based in US and Europe. So these manuscripts from Iran's has to be assigned to me, okay? So in that case, I'm dealing with perovskites, and out of 360 per year, I think I'm handling at least around 20 manuscripts on different composition of perovskites. So you see, there's a lot of studies going on in this area. And so by changing this little bit of some other components, you have different perovskite membranes. And this is one of the just examples which was published in 2011. We have zeolite membranes. Zeolite membranes, and zeolite is coming from Greek, and it means boiling stones, okay? Meaning that you have a lot of porosity in the zeolites. Okay? So this is a natural the stone, but mimicking this natural boiling stones, they started to make different types of zeolites. Okay? So there are a lot of inorganic chemists working in this area, and I also receive at least 20 to 30 manuscripts about the zeolite membranes in every year, okay, with different compositions. They have inorganic zeolites, but recently they have inorganic organic zeolites. Okay? Inorganic organic frameworks called GIF, or metal and organic frameworks with mimicking these crystal structures. Mimicking these crystal structures is called the MOF. So GIF and MOFs are very recently been focused on in many inorganic chemistry particularly, and there's a lot of chances to have very good membranes. We also in Korea a lot of inorganic chemists, and for some chemists are trying to make a CO2 selective one or hydrogen selective MOF, hydrogen selective ones, or stuff like that. So if you are using those very novel GIF or MOF or whatever, they can form the very nice membranes. But in small size, not in the larger scale, they are still in the laboratory scale, not in the commercial scales. But anyway, there will be good future in zeolite the area if you are able to make in a very larger scale in economical way, because it needs a lot of efforts. It's very costly. It's high in price. This bothers about the commercialization of the zeolite membranes, but zeolite powder itself has already been commercialized. Zeolite powder has been commercialized. It's been used as a catalyst in chemical processes and chemical engineering processes, but membrane is a little different from powder, as you all know, right? So now a lot of efforts has been focused on zeolite membrane formation, MOF membrane formation, GIF membrane formation, but still a little bit long way to go compared to the polymer cases. You have a lot of other types of zeolites. One of the nice feature of this zeolite is that you have a very, very defined, three-dimensional pore structures with the known cavity sizes or pore sizes. Cavity sizes or pore sizes ranging, in some Armstrong levels, like 3 Armstrong levels or 3.5 Armstrong level. So it will be able to actively separate the even gases. Okay? About 10, 15 years ago, it was not possible, but they can make a small piece of zeolite membrane with this crystal structure, with this 3-dimensional structure, and be able to make nice membranes in a small area. Okay? In order to make nice zeolite membranes, there's a lot of efforts that needs to be done. Okay, I do not want you to read this, but you need to make a zoll and gels and sinter them, and process to make this zeolite is a little complicated, and even they may use a microwave in order to make frames. This is one example of making the zeolite membranes. And in order for your, the ion conductive the capability, in some cases we have metal membranes. Metal membrane and perovskite membrane has a similarity in terms of the ion conductivities. Ions are conducting through this membrane. And this picture is one of the example of palladium membrane. Palladium is a very expensive metal membrane with a very thin thickness. And what you do is that you have water and CO2 and hydrogen at high temperature. Okay? This palladium membrane can be used in the IGCC process, integrated gasification coal-fired combined process, meaning that IGCC process has been used to make the electricity from your clean coals. Meaning that when you have a coal, if you fire this coal to make a heat, and this heat will, in heating your water, to generate the steam, and the steam will, move the turbines to generate the electricity, and that's the traditional way of making the electricity from your coal-fired power plants. Okay? So coal-fired heat and steam generation and turbine movement and electricity is a coal-fired power plant process. But one of the issue about this traditional coal-fired power plant is flue gas. Okay? Flue gas coming from the chimney contains about 15% CO2, 80% nitrogen, and a few percent oxygen and water. CO2 is a problem, we believe. Well, some may not believe about the CO2 problems, but we believe that the CO2 is a problem. So we wanted to capture the CO2 from these coal-fired power plants. But if you have coals and heat them up, okay, with a catalyst, and generate the hydrogen and CO2 or CO, this is what they call the syngas process, okay, at high temperature and high pressure, usually over 300 degrees C and 20 bar, you generate the hydrogen and CO or CO2, so that this is the feed mixture here. You have a CO2, you have CO and hydrogen. Hydrogen is much smaller in size, okay, like a 2.8 Armstrong, whereas the CO is about 4 Armstrong or something like that. CO2 is about 3.3. So you can have a hydrogen coming out from your membrane, possibly. But when you separate the hydrogen from your mixture of CO2 and hydrogen, this hydrogen can be collected, and hydrogen could be fed into the reactor, and you can generate the heat, because hydrogen has much higher the heating power, so that it will heat them up. The steam, you can generate the steam and make the turbine and make the electricity. If you use this hydrogen as a source for your energy, then there is no chance to generate the CO2, right? Although you start from your coals, you generate the hydrogen as use as fuels to make the electricity, whereas your CO2 is separated before your turbine movement. Okay? So this is what they call the IGCC process, or pre-combustion process, and palladium can separate the hydrogen from your mixture of your hydrogen and CO2 here in this case. Now, the mechanism of separation is that you have a hydrogen, but hydrogen is dissociated into the protons or ions, so that there is a diffusion through this palladium. But the thickness of the palladium should be as small as possible, because the thickness will be acting as a barrier for your transport. So it should be as thin as possible. And this hydrogen ion will be dissociated or dissolved from the opposite side of your membrane interface. And the ions get together to become molecule to remain as molecules, hydrogen molecules. So this way, the hydrogen ion is transporting through this palladium membrane, and this is one example of ion transporting membrane as well too. Anyway, the palladium has been known to be very active hydrogen transporting membrane, particularly at high temperature, okay? Not in low temperature. It should be above at least 400 degrees C, 400 degrees C for your ion transporting capability of this palladium, and also high pressure. So a lot of studies has been done about the palladium itself and palladium alloys, because palladium is expensive metals. They try to reduce the cost of the palladium with the blending with other metals. Okay? Now, the second metal or third metal is very important, so that they're still reporting, particularly in JMS, at least maybe 10 per year about this metal membrane is assigned to me, so I'm handling about this. So this hydrogen can be used to generate the power, or can be used as a fuel cells, such as the polymer electrolyte membrane fuel cells. I don't want to iterate about the hydrogen economy, but anyway, the palladium or palladium alloys are very important materials for your hydrogen separations. Okay, so that's about the membrane materials. And if you have any question, please, or if not, then I think we can continue on next Wednesday, continue about the membrane preparation and characterizations.